This section has three special cases of factoring: difference of squares, perfect square trinomials, and then sum and differences of cubes. So we start with the difference of squares. Difference means you subtract, right? The difference of 10 and 4 is 6 because 10 minus 4 is 6. In this case, most of them will be perfect squares, although technically to do a difference of squares, they don't have to be perfect squares. It's just the pattern that holds. And there's no middle term when you're factoring a difference of squares. So when you go to do some factoring and you see an x squared minus 4, essentially you're looking for two numbers that multiply to be negative 4 and add up to 0, which means they have to be the same number with different signs in order to add up to 0. So in this case, we would be thinking about a 2 and a negative 2. So a positive 2 and a negative 2, right? FOIL it back out. You'll get an x squared minus 2x plus 2x zeros out. 2 times negative 2 is negative 4. So this fits our difference of squares pattern up here that says if I factor that difference of squares, I get the square root of each, right? So the square root of a, square root of b. Right, there we go. There's our square root of a squared. There's our square root of b squared. One gets a plus, one gets a minus, and we're done. All right, look at number 2. Two perfect squares, a minus sign between them. So the square root of 9x squared is 3x. Square root of 25 is 5. One gets a plus, one gets a minus. FOIL it back and see if it works. I get a 9x squared minus 15x plus 15x zeros out. 5 times negative 5, negative 25. Hey, number 3 looks a little bit different. Not terribly different. 25x squared is a perfect square. So is 49y squared. They got a minus in between them. So the square root of 25 is 5, so I get a 5x. Square root of 49 is 7. Square root of y squared is y, so I get a 7y. One gets a plus, one gets a minus. FOIL them back and you'll see you get a 25x squared. You get a minus 35xy and a plus 35xy, so they zero out. Minus 49y squared. All right, last one's written in a different order, but it's still a difference of two squares. Square root of 100 is 10. Square root of x is x. Or square root of x squared is x. One gets a minus, one gets a plus. So I get 100 plus 10x minus 10x goes away, minus x squared. So like I said, the difference of squares pattern technically works for things that are not perfect squares. So if I said factor x minus 5 with a difference of squares, or how about this? 3x squared minus 5 with a difference of squares. You could do it. You would get square root of 3 times x minus the square root of 5 and square root of 3 times x plus the square root of 5. And when you multiply them together, it really does work. The square root of 3 times the square root of 3 is 3, so you get a 3x squared plus the square root of 15 times x minus the square root of 15 times x. And your last term just becomes minus the square root of 25, which is minus 5. So you technically can apply a difference of squares pattern to something that is not a set of perfect squares. But in this course, at this level, in this book, you're going to be doing things that mostly involve perfect squares. The big note in this one is that there is no sum of perfect squares, right? There is a difference of squares, but over the set of real numbers, there's no sum of squares. Because if I said try factoring x squared plus 25, you're looking for two factors that multiply to be 25 and add up to 0 and have the same sign, right? If they multiply to be 25, they have to have the same sign. Well, 5 and 5 will multiply to be 25. Negative 5 and negative 5 will be multiplied to be 25. But neither of those groups will add up to be 0, right? 5 plus 5 is 10. Negative 5 and negative 5 is negative 10. So assuming we're dealing only with real numbers here, in other words, not imaginary numbers, which we will get to later in the course, there is no sum of squares pattern. So x squared plus 25, you're done. Not factorable. All right, perfect square trinomials. We had seen this before when we were foiling things out. This is the other version of it. So this is the version where you're given a trinomial, you're going to factor it. You notice that there's a little pattern here. If you take half of 18 and square it, you get 81. So half of 18 is 9. 9 squared is 81. So if there's a 1 before that x squared, that's a real quick way of figuring out, do I have a perfect square trinomial? So I claim then that I can write this as x plus 9 times x plus 9. Square root of 81 is 9. Multiply x times x, I get x squared, plus 9x is 18x. 9 times 9 is 81. And this I can also write as x plus 9 squared like that. Right? Perfect square trinomial. Trinomial had 3 terms. I can write it as a perfect square. So I can do the same thing for number 2. You notice the square root of 36 is 6. And if I write this as x plus 6 times x plus 6, I get x squared plus 6x plus 6x gives me 12x. And then 6 times 6 is 36. So again, the little trick was half of 12 was 6. 6 squared is 36. Does it work for the third one? Third one is a little bit different because you notice there's a number before that x squared. So if I'm trying to factor something and I'm not sure where to start, right? I got a 4x squared minus 28x plus 49. Could I use the AC method for this one? Yes. 4 times 49 is a big number. It's like 196. So I'd be looking for factors of 196 that add up to be negative 28. Maybe I don't need to do that. I notice I got a 4x squared. I notice I got a 49. Just a hunch. I'm going to go, well, what if square root of 4x squared is 2x, square root of 49 is 7, and because of the negative before the 28, I'm going to make them both negative. See if it works. 2x times 2x is 4x squared, minus 14x, that's my outside and inside, that gives me a negative 28x, negative 7 times negative 7, positive 49. So this thing factors as 2x minus 7 squared. Look at the last one. Last one has both x's and y's in it. Again, they're both perfect squares, so I'm going to call the first one, the square root of 49 is 7, the square root of x squared is x. How about the 9y squared? 3y. What signs do I put in? Well, this says minus, so I'm going to put a minus. Does it work? 49x squared minus 21xy minus another 21xy gives me a minus 42xy. Negative 3y times negative 3y, 9y squared. So it's good. I can also write this as 7x minus 3y squared. And then the last pattern to work on is sum and difference of cubes. This one might take a little memorizing. I don't know if you've seen sum and difference of cubes before, but look at my first 2 examples. They're basically the same problem, but I changed the sign. So I've got an x cubed plus 8. X cubed is a perfect cube. 8 is a perfect cube. Perfect cube meaning numbers like 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. So these numbers get pretty big pretty fast. All right, so look at the pattern here. It says a cubed plus b cubed is a plus b times a squared minus ab plus b squared. Notice the patterns between them. Each of these both starts with an a and a b, a squared, ab, and b squared, right? The pattern underneath it is the same thing, a b, a squared, ab, b squared. How do the signs go in the one on the top? So I started with a squared, or a cubed plus b cubed. So if I want a plus, it goes same sign, opposite sign, positive sign. Look with the minus. Same sign, opposite sign, positive sign. So if you wanted to fit the pattern, the cube root of x to the third is x. The cube root of 8 is 2. So I've got an a and a b, a squared, ab, b squared. How do the signs go? Same sign, opposite sign, positive sign. I'm done. Those are my factors. It's tempting to try to factor that x squared minus 2x plus 4 because it just looks like something that we should be able to factor, but it turns out we can't. Right? X squared minus 2x plus 4 doesn't factor over the set of real numbers. All right, let's try the x cubed minus 8. Again, the cube root of x to the third is x. The cube root of 8 is 2, so I have an x and a 2, an x squared, a 2x, right, just the product of these two terms, and a 4. The big difference is how the signs go. This is x to the third minus 8. So same sign, opposite sign, positive sign. All right, let's try a couple more. For the first one, for number 3, the cube root of 27x cubed, cube root of 27 is 3, because 3 times 3 times 3 gives me back 27. Cube root of x cubed is just x. Cube root of 64 is 4, because 4 times 4 times 4 gives me 64. So how does it go? A 3x and a 4. A 3x squared, which means square the 3 and square the x squared. The AB term is multiply your 3x by 4. So 3x times 4, 12x. And then 4 squared is 16. How did the signs go? It started with a minus, so minus, plus, plus. And then I'm done. Again, it looks like I should be able to factor that 9x squared plus 16. Doesn't work that way, though. Even if you try that difference of squares pattern, it's going to give you a number on the inside that's not a 12x. All right, for number 5, let's skip down to number 5. What's weird about number 5? Nothing except the numbers are big. Cube root of 27, oh, I got a p in there. 27p to the third, the cube root is 3p. How about a 343? Well, I'd put up there that 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216. How about 7 to the third? Oh, 7 to the third is 343. So the cube root of 343 is 7. So my terms have a 3p and a 7. What is the second term? It's the a squared, so 9p squared. Multiply the inside, so 3p times 7, 21p. 7 times 7 is 49. How do the signs go? Same sign, opposite sign, positive sign. All right, let's tackle a couple from the last slide, and then we're done with this section. For the first one, a 98 and a 32, neither of them are perfect squares. And didn't I say that a lot of the ones in this section are going to follow perfect squares? The first thing you always do for these is you look for a common factor. So I'll notice that 98 and 32 are both even, so I'll start by pulling out a 2. Half of 98 is 49. Half of 32 is 16. Oh, look, now they're both perfect squares. All right, the square root of 49x to the fourth is 7x squared. Square root of 16y squared is 4y. One gets a plus, one gets a minus. All right, so 49x to the fourth minus 28x squared y plus 28x squared y zeroes out. My last term is negative 16y squared. One of the reasons I picked difference of squares, and we're going to do more of this in the next section, is because I only had 2 terms. And they were perfect squares. If there were 2 terms in perfect cubes, then I'd be looking at sum and difference of cubes. All right, for number 2, first thing I would do is I would pull out that 3. That leaves me with a p squared. 24 divided by 3 is 8, so minus 8p plus 16. Right, this looks to me like a perfect square trinomial. Why? Because if I take half of 8, I get 4. Square it, and I get 16. Suppose I didn't see that. Suppose I said, all right, well, p times p is p squared. I'm looking for 4 times 4 to be 16, but I want them both to be negative, so like that. Try it out. P squared minus 8p plus 16, which means I can write my answer as 3p minus 4 squared. Ooh, look at number 3. Number 3 looks a little messy. Well, that's all right. Always look for common factors first. So between a 24 and a 375, I see at least a 3 that I can pull out. I also notice that they both have an m. So let's pull out a 3m. 24 divided by 3 is 8. I got a k cubed. The m's go away. 375 divided by 3, I do not know off the top of my head. Let's throw it on a calculator. 375 divided by 3, 125. So minus 125, when I pull out that m, it becomes m to the third. Now I've got two things with a minus sign. It's a difference of something. This one's a difference of cubes, because you notice I've got an 8 and a 125. They're both perfect cubes. K cubed and m cubed, again, perfect cubed. So I got a 3m. This is the one where it's got 2 parts and 3 parts. The cube root of 8 is 2. The cube root of k cubed is k. In the second part, the cube root of 125 is 5. Cube root of m to the third is m. So there's our a and our b. How does the pattern go in the second part? It's the a squared, so square root 2k, and you get a 4k squared. There's an AB term, which means multiply the two numbers together. So a 2k and a 5m gives me a 10mk, or a 10km. And then 5m squared gives me 25m squared. And I'm just left with signs. We started with a minus, so it goes same sign, opposite sign, positive sign. And don't forget that 3m at the beginning. That's part of the answer as well. All right, last one. What happens to that problem down the bottom? Well, the first thing I do is I look to see if I can find any common factors. I got a 16, a 72, and an 81. They have a lot of common factors, but none all in common to each other. All right, 16 has factors like 1, 2, 4, 8. 72 does contain factors like 8 and 4, but the 81 has factors of like 3 and 9 and 27. So the only thing then left I'm going to look at are the A's and B's. So everybody's got at least one A and one B, so let's factor out an AB. And I'm left with 16A squared plus 72AB plus 81B squared. And now this is looking more like one of those perfect square trinomials because I've got a perfect square at the beginning and end. So I'll leave my AB. Square root of 16a squared is 4a. Square root of 81b squared is 9b. FOIL it back and see if it works. Sure enough, the 16a squared at the beginning works. The 81b squared at the end works. Let's see if the insides work. 4a times 9b is 36ab, and I got another 36ab from the inside. Beautiful. That's my middle term. So I can write my answer as AB times 4a plus 9b squared. If I have two of the same term multiplied together, it's a square. So because I have 4a plus 9b times itself, it's 4a plus 9b squared.